This is the final module of the chapter Hermite polynomial. In this module 3, we will learn about the orthogonal properties of the Hermite polynomials along with the proof. Then we will look into the application of the orthogonal property in various problems. Orthogonal property of the Hermite polynomials. So, Hermite polynomials are orthogonal over minus infinity to plus infinity with respect to the weight function e to the power minus x square. Mathematically, this means integration minus infinity to plus infinity e to the power minus x square h n x h m x dx is equal to 0 if m not equal to n and is equal to root pi 2 to the power n into n factorial if m equal to n. To start the proof, we start with the generating functions given by equation 1 and 2, which is summation n equal to 0 to infinity h n x t to the power n by n factorial equal to e to the power 2 t x minus t square, and summation m equal to 0 to infinity h m x s to the power m by m factorial equal to e to the power 2 s x minus s square. Multiplying 1 and 2, we will get summation n equal to 0 to infinity summation m equal to 0 to infinity h n x h m x divided by n factorial m factorial t to the power n into s to the power m equal to e to the power 2 t x minus t square plus 2 s x minus s square given by equation number 3. We now multiply both sides of 3 by e to the power minus x square and then integrate it with respect to x from minus infinity to plus infinity, and we will be getting equation 4, which is summation n equal to 0 to infinity summation m equal to 0 to infinity integration minus infinity to plus infinity e to the power minus x square h n x h m x t to the power n s to the power m divided by n factorial m factorial is equal to integration minus infinity to plus infinity e to the power minus x square plus 2x t plus s minus t square plus s square dx. We next integrate the right hand side of 4, which is this expression, and if you do that, we will get integration minus infinity to plus infinity e to the power minus x square plus 2x t plus x minus t plus s whole square into e to the power t plus s whole square minus t square plus s square dx. So, what we have done here is we have taken the term minus t plus s whole square and adjusted it with plus t plus s whole square, so that if you simplify this, you will be getting exactly what is in the exponential of equation 4. Further simplification gives integration minus infinity to plus infinity e to the power minus x minus t plus s whole square dx, which is equal to e to the power 2 t s root pi. Expanding e to the power 2 t s in exponential, we will get this is equal to root pi summation n equal to 0 to infinity 2 t s whole to the power n by n factorial given by equation 6, and this can be written as summation n equal to 0 to infinity 2 to the power n into root pi divided by n factorial t to the power n s to the power n given by equation 7. If m is not equal to n, we equate the coefficient of t to the power n s to the power n from both sides of 7, and we will get integration minus infinity to plus infinity e to the power minus x square h n x h m x dx is equal to 0. Let us recall 7. So, what we get here is t to the power n s to the power n, and on the left hand side we have e to the power minus x square h n x h m x into t to the power n s to the power m. Now, when n is not equal to m, the right hand side we do not have any term of m. So, the coefficient of right hand side of t to the power n s to the power m is 0, because we do not have any m term in the right hand side. Whereas, on the left hand side the coefficient is minus infinity to plus infinity e to the power minus x square h n x h m x dx divided by n factorial into m factorial, and on the right hand side it is equal to 0, and hence this expression is equal to 0. And therefore, we get expression 8, which is minus infinity to plus infinity e to the power minus x square h n x h m x dx is equal to 0. However, when m is equal to n, then we have to equate the coefficient of t to the power n s to the power n from both sides of 7, and we will get, to the right hand side the coefficient of t to the power n s to the power n is 2 to the power n root pi divided by n factorial, and to the left hand side we replace this m by n, and we will get e to the power minus x square h n x h n x, which is h n x whole square divided by n factorial and m factorial, and hence we will get 1 by n factorial into n factorial from minus infinity to plus infinity e to the power minus x square h n x whole square dx is equal to 2 to the power n root pi by n factorial. Rearranging the terms, we get our required result as integration minus infinity to plus infinity e to the power minus x square h n x whole square dx is equal to 2 to the power n into n factorial into root pi, given by equation 10. Hence, the conclusion is that when m is not equal to n, integration minus infinity to plus infinity e to the power minus x square h n x h m x dx is equal to 0, and when m is equal to m, it is equal to 2 to the power n into n factorial into root pi, which is the orthogonal property of the hermite polynomial. We have just learned the orthogonal property of the hermite polynomial along with a rigorous proof. We will now look into the application of this orthogonal property in various problems of hermite polynomials. Let us now look into the application of this orthogonal property. In example 1, we have to show integration minus infinity to plus infinity x square e to the power minus x square h n x whole square dx is equal to root pi 2 to the power n into n factorial into n plus half. Please recall the recurrence relation given by h n plus 1 x is equal to 2x h n x minus 2n h n minus 1 x, given by equation 11. We multiply 11 by x and x square, and we get respectively equation 12 and equation 13. We next replace n by n minus 1 and n plus 1 successively in 12. That is, we replace this n by n minus 1 and we get the result x into h n minus 1 x is equal to n minus 1 h n minus 2 x plus half of h n x, given by equation 14. Next, we replace this n by n plus 1 and we will getting x h n plus 1 x is equal to n h n x plus half of h n plus 2 x. given by equation 15. We next substitute the value of h n minus 1 x and h n plus 1 x from equation 14 and 15 in equation number 13. So, as told before, using 14 and 15, equation 13 becomes 8x square h n x is equal to n times n minus 1 h n minus 2 x plus half of h n x plus half of n plus 1 h n x plus half of h n plus 2 x, which on simplification gives x square h n x is equal to n into n minus 1 h n minus 2 x plus 1/4 of h n plus 2 plus n plus half h n x, given by equation 16. We next multiply 16 both sides by e to the power minus x square h n x and integrate with respect to x from minus infinity to plus infinity. And as you do that, you will be getting integration minus infinity to plus infinity x square e to the power minus x square h n x whole square dx is equal to n into n minus 1 integration minus infinity to plus infinity e to the power minus x square h n x h n minus 2 x dx plus 1/4 integration minus infinity to plus infinity e to the power minus x square h n x h n plus 2 x dx plus n plus half into integration minus infinity to plus infinity e to the power minus x square h n x whole square dx, given by equation 17. We next use the orthogonal property. So, please note the first term of 17, here it is n and it is n minus 2. So, this is not equal to this, and hence this whole expression will be equal to 0. In the second expression of 17, we have the same logic that this n is not equal to n plus 2, and hence the integration of this expression will be equal to 0. However, in the third expression, when both are same, that is h n x whole square, we use the orthogonal property and we will be getting n plus half into root pi into 2 to the power n into n factorial, given by equation 18. And hence we conclude that integration from minus infinity to plus infinity x square e to the power minus x square h n x whole square dx is equal to n plus half root pi 2 to the power n into n factorial, which is our required result. In our next example, we will show, rather we will evaluate the value of the integral from minus infinity to plus infinity x e to the power minus x square h n x h m x dx. Now, from the recurrence relation, we get h n plus 1 x is equal to 2x h n x minus 2n h n minus 1 x. Rearranging the terms, we will get x h n x is equal to n h n minus 1 x plus half of h n plus 1 x, given by equation 19. We next multiply equation 19 by e to the power minus x square h m x, and then we integrate with respect to x both sides from minus infinity to plus infinity. And if you do that, we will get integration from minus infinity to plus infinity x e to the power minus x square h n x h m x dx is equal to n times integration from minus infinity to plus infinity e to the power minus x square h m x h n minus 1 x dx plus half of integration from minus infinity to plus infinity e to the power minus x square h mx h n plus 1 x dx. Therefore, we get integration from minus infinity to plus infinity x e to the power minus x square h n x h m x dx is equal to n root pi 2 to the power n minus 1 into n minus 1 factorial Kroneker's delta n minus 1 m plus half of root pi 2 to the power n plus 1 into n plus 1 factorial Kroneker's delta n plus 1 m. Please note, if m is equal to n minus 1 in this case, then the value will be 1 and otherwise the value is 0. So, we express this expression with the Kroneker's delta because we are not sure about the value of m in this case. On further simplification, we get our desired result as integration minus infinity to plus infinity x e to the power minus x square h n x h m x dx is equal to root pi 2 to the power n minus 1 into n factorial Kroneker's delta n minus 1 m plus root pi 2 to the power n into n plus 1 factorial Kroneker's delta n plus 1 m. In our next example, we will use Roderick's formula for the hermite polynomial h n x, and then by integrating it by parts iteratively, we will show that the integration from minus infinity to plus infinity e to the power minus x square h n x h m x dx is equal to 0 if m not equal to n and is equal to 2 to the power n into n factorial into root pi if m is equal to n. So, Roderick's formula for the hermite polynomial is given by h n x is equal to minus 1 whole to the power n e to the power x square nth derivative of e to the power minus x square, which can be written as e to the power minus x square h n x is equal to minus 1 whole to the power n into the nth derivative of e to the power minus x square given by equation 24. Therefore, psi is equal to integration from minus infinity to plus infinity minus 1 whole to the power n e to the power minus x square h n x h m x dx is equal to integration minus infinity to plus infinity minus 1 whole to the power n e to the power nth derivative of e to the power minus x square into h m x dx. Integrating by parts, we will get this is equal to minus 1 whole to the power n multiplied by h m x n minus 1th derivative of minus x square from minus infinity to plus infinity minus integration minus infinity to plus infinity n minus 1th derivative of e to the power minus x square d dx of h m x dx. Substituting the limits, we will get the first term of equation 27 to be 0 because of the presence of e to the power minus x square, and we are left with the term minus integration minus infinity to plus infinity n minus 1th derivative of e to the power minus x square multiplied by d dx of h m x dx given by equation 28. Integrating by parts iteratively, we will come to equation number 29, which is integration from minus infinity to plus infinity nth derivative of h m x e to the power minus x square dx. Now, h m x is a polynomial of degree m. If n is greater than n, then the nth derivative of h m x is equal to 0. which is true if you just substitute some positive values, some positive integer values of n and m. For example, if you try to find the second derivative of x, the answer is obviously 0. So, this is exactly the case here. So, we conclude if n is greater than m, then from equation 29 psi is also equal to 0. And since psi is symmetrical in m and n, it follows that if m is greater than n, psi is also equal to 0. And hence, we conclude from equation 31 and equation 32 that psi is equal to 0 for m not equal to n. But if m is equal to n, then from 29 we get psi is equal to integration minus infinity to plus infinity the nth derivative of h m x e to the power minus x square dx. Now, the nth derivative of h n x is equal to 2 to the power n into n factorial. Using this formula, we will get the above integral is equal to integration from minus infinity to plus infinity 2 to the power n into n factorial e to the power minus x square dx. Further simplification gives psi is equal to 2 to the power n into n factorial into root pi, where m equal to n, where we use the value of the integral integration minus infinity to plus infinity e to the power minus x square dx is equal to root pi. And hence, from equation 33 and equation 34, we conclude that psi is equal to from minus infinity to plus infinity e to the power minus x square h n x h m x dx is equal to 0 if m not equal to n and is equal to 2 to the power n into n factorial into root pi if m is equal to n. In our next example, we will show that summation k equal to 0 to n h k x h k y divided by 2 to the power k into k factorial is equal to h n plus 1 y h n x minus h n plus 1 x h n y divided by 2 to the power n plus 1 into n factorial into y minus x. Now, from the recurrence relation, h n plus 1 x is equal to 2 x h n x minus 2 n h n minus 1 x, we can rewrite it as x h n x is equal to n h n minus 1 x plus half of h n plus 1 x given by equation 35. We replace x by y in equation 35 and we will get y h n y is equal to n h n minus 1 y plus half of h n plus 1 y given by equation 36. We next multiply equation 36 by h n x and 35 by h n y, and subtracting we will get y minus x h n x h n y is equal to half of h n plus 1 y h n x minus h n plus 1 x h n y minus 2 times h n minus 1 x h n y minus h n minus 1 y h n x given by equation 37. Next, we put n equal to 0, 1, 2 dot 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 n minus 1 n successively in equation 37, and we will get y minus x h 0 h 0 y equal to half of h 1 by h 0 x minus h 1 x h 0 y minus 0 given by equation 38. Y minus x into h 1 x h 1 y is equal to half of h 2 y h 1 x minus h 2 x h 1 y minus 2 times h 0 x h 1 y minus h 0 y h 1 x given by equation 39, and likewise we will get equation number 40, equation number 41 and equation number 42. Next we multiply equation 38, equation 39, equation 40, equation 41 and equation 42 respectively by 1 by 2 into 1 factorial, 1 by 2 square into 2 factorial, 1 by 2 to the power cube into 3 factorial, dot 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 1 by 2 to the power n minus 1 into n minus 1 factorial, and 1 by 2 to the power n and n factorial, and then we add all these results. And if you do that, you will get this is equal to y minus x summation k equal to 0 to n h k x h k y divided by 2 to the power k into k factorial equal to h n plus 1 y h n x minus h n plus 1 x h n y divided by 2 to the power n plus 1 into n factorial. And in the next step, all you have to do is divide the right hand side by y minus x, and we get our desired result as given in equation 44. Summing up, we have started with the hermite equation, and we have shown that the hermite polynomials are the solution of the hermite equations. Next, we have seen the generating function of the hermite polynomials. After that, we have learned about the orthogonal property of the hermite polynomials. The problems we have done gives overall idea of the exposition of hermite polynomials in applications. I hope it is clear to you. Thank you.